In this video, we will learn different kinds of arithmetic operations on complex numbers. We will first start with the Cartesian form of complex numbers and see different operations of additions, subtraction, multiplication and division. Later on, we will use exponential form of complex numbers and see these operations and see how these operations are simplified in case of exponential form. So let's start with the Cartesian form of complex numbers. So I have given two complex numbers. One is let's say z1, which is equals to a plus iota b, and my second complex number is z2, which is equals to c plus iota d. And I have to first write addition between these two complex numbers. And also I will write subtraction, because addition and subtraction are basically the same operation with different signs. So if I add z1 and z2, then I will be adding both of the real terms, and also I will be adding both of the imaginary terms. So my result will be a plus c, both of the real terms addition, plus iota, both of the imaginary terms addition, b plus d. Similarly, in case of subtraction, my result will be the same but with different sign. My result will be a minus c plus iota b minus d. Now let's see how to multiply two complex numbers. I have to multiply z1 with z2, and my answer will be ac minus bd plus iota ad plus bc. You might be wondering that from where I have get this result. So let's verify. I have to multiply z1 with z2. To that end, I will multiply a with c. So this will be ac. Now I have to find my other real term. If I multiply a with iota d, it will be imaginary term. If I multiply iota b with c, it will also be an imaginary term because it will have an iota in it. However, when I multiply iota b with iota d, then iota square is equals to minus 1, and there will be no more an iota. So that's why I will say when iota b times iota d is minus bd. So these are my two real terms. Now I will write all of my imaginary terms. I multiply iota b with c, so I will have bc, and I multiply a with iota d, so I will have ad. And thus we have verified that this result was indeed correct. The next arithmetic operation we want to learn about is division. So I have to divide z1 with z2, and my result will be ac plus bd. This will be my real term in the denominator, plus iota bc minus ad, divided by c square plus d square. So let's verify this result by deriving it. So I start with z1 divided by z2. Hence my numerator will be a plus iota b and my denominator will be c plus iota d. I do not wish to have a complex number in my denominator, so I multiply numerator and denominator with c minus iota d. And this will be equals to, in the denominator I will have c square minus iota d whole square, where iota d whole square will be plus d. So in the denominator I will have c square plus d square. In the numerator I have these two numbers, that is, I am multiplying these two numbers. The only difference is this sign. So I have to take care of this sign. Because in this case I have positive sign, here I have negative sign. Otherwise my result will be the same. So I multiply a with c, and ac is my one real term. Second real term will be when I multiply iota b with minus iota d, and that will be equals to plus bc dd. Then I will have to write my imaginary terms, which will be that I multiply a with iota d and I multiply iota b with c. So first let's multiply iota b with c, so that I have first a positive number. I will have here bc and minus ad, and this verifies that this result was indeed correct. So we are done with different arithmetic operations when our complex numbers are in Cartesian form. Now let's see what will happen if our complex numbers are in exponential form. So I've given z1. In this case, in exponential form, I say my z1 is equals to r1 Euler constant raised to power I theta 1, and in this case my z2 is equals to r2 times Euler constant raised to power iota theta 2. Addition and subtraction in this case are not much interesting, because we will only have a plus sign between r1 Euler constants raised to power I theta 1 plus r2 raised to power Euler constant raised to power I theta 2. So my addition and subtraction is kind of boring in this case, because z1 plus z2 will be equals to r1 Euler constant raised to power I theta 1 plus r2 times Euler constant raised to power I theta 2. But my multiplication and division are relatively much more interesting in this case. So let's look at the multiplication. So if I multiply z1 and z2, then I will have r1 times r2, and these two terms when multiplied, then their power will add. So I will have Euler constant raised to power I theta 1 plus I theta 2, and this can be simplified to r1 dot r2 times Euler constant raised to power iota theta 1 plus theta 2. So that's much more interesting. So similarly, the operation of division in this case is much more easier as compared to operation of division in that case. So if I divide z1 with z2, my result will be r1 over r2 Euler constant raised to power I theta 1 minus I theta 2. and I can take basically iota out, so I can write it like iota theta 1 plus theta 2. And how I get this result is that when we basically write r1 over r2 and we write Euler constant raised to power I theta 1 in the numerator, and the denominator we write Euler constant raised to power I theta 2. When I take this in the denominator, then I will have, instead of I theta 2, I will have in the denominator Euler constant raised to power minus I theta 2. And because these two terms are being multiplied, so their powers will add. So we have added their powers. So by the way, there we should have minus sign, not plus sign. Yeah. So otherwise, this result is correct. Similarly, there are many other very interesting results in case of exponential form of complex numbers. Let's quickly write those results also. So there are 4 very interesting results. Let's list them. Number 1, if I say argument of z1 times z2, we have defined what argument means. It's the angle between x-axis and the position vector. Then it will be equals to theta 1 plus theta 2, and that is in fact will be equals to argument of z1 plus argument of z2. So basically it's very simple in this case. Second result is that if I say argument of z1 divided by z2, then this will be equals to theta 1 minus theta 2. That means it will be equals to argument of z1 minus argument of z2. My third important result is if I say modulus of z1 and z2, that will be equals to r1 over r2. That means it is equals to modulus of z1 divided by modulus of z2. My fourth and the last important result is that if I say modulus of z1 and z2, then it will be equals to r1 times r2, and that means it is equals to modulus of z1 times modulus of z2. So that is it for this video. See you in the next video.